Hey astronomy kids, Mr. Johansson here. Today, we're gonna kill some stars. Pretty heavy. Well, how do you kill a star? You can't kill a star. But stars die of their own accord. So how does a star die would be a better question. Come on over to the board, let me show you. All right? So, boom, got a star. Look at that. Big. How big? Here you go. There's Earth. Star's pretty big. That's just our sun. Some suns are smaller, some suns are much bigger. And how much mass they have, not the size of them, but how much mass they have, that's going to determine how they die. So why don't we work our way up? A low mass star and a high mass star. The Crash Course Astronomy field plate will take you through all the different types. Please pay close attention to that. And it's amazing. It is amazing. It's the most incredible thing in the universe, just about, other than maybe the birth and function of the universe and galaxies and stuff. How a star works is incredibly important to how everything else in the universe works. So yeah, learn this stuff. It's important. So the question that we're on is question 14, and it says, what are the three potential objects produced by a dying star? Describe each. What are the two ledges that might hold back gravitational collapse? I got a lot of stuff to do. Anyway, let's do the quick version of it. So inside a star, you have the core. What are the conditions in the core? Incredibly massive, incredibly dense, so much mass. And the gravity, because of that mass, is pulling it so hard. The density is incredible. What else is incredible? The temperature. It's been fusing hydrogen to helium for ages. And the core has been getting hotter and hotter and hotter for ages. It's incredibly hot now. And the thing about it is it has just finished burning all the hydrogen it can find into helium. Okay, so what happens to the star at that point, right? Now, this is a general case. In the super low mass stars, as Phil Plait will show you, you have a churning motion all through the star. So what you end up with is an entire star made of helium. In that case, once it no longer has nuclear fusion to push outward, the star collapses down tremendously small. This happens for a variety of stars, both the smaller ones and stars like our sun. But the core will collapse. What will stop the core collapse? Well, you might be tempted to say, well, the atoms are going to bump into each other. Well, that's how come I'm not falling through the floor. So stopping the core collapse is not really a valid excuse here. It has to do with quantum mechanics, and it has to do with really something called electron degeneracy pressure. That's what's going to stop this core collapse. So the core will collapse down to an extremely tiny object. Remember when I showed you Earth in comparison to it? That's what's going to happen to the core. Now, what's going to happen to the outer part of the star when this happens? It's going to be fluffed off and form a planetary nebula. Check out some pictures of them. They're probably the most beautiful objects in space. But for the rest of it, I can erase this whole thing now and just put down, I ought to do it in white because this thing is shining so brightly. It's got a great deal of the mass of the star now in an object the size of the Earth. That's incredible. And it's supported by something called electron degeneracy pressure. And essentially, the electrons are jumping about trying to fill quantum holes, and they have to jump at a particular speed. And it is that all of that incredible jumping that supports this. Well, how fast can electrons go? Do they have a maximum speed? Of course, speed of light. They cannot exceed that. So, how much crushing force they have determines their speed. So what if the crushing force left behind exceeds the electron degeneracy pressure's ability to push outwards? In other words, it would be asking the electrons to move faster than the speed of light. It's not going to happen, so that means this core would keep collapsing. So we'll get to that in a second, but to get to that, let's talk about the death of a higher mass star. Right? In a higher mass star, it's not just that we have a core where the hydrogen has all burned into helium. What happened then is the core collapsed and there was enough mass to force the ignition of helium. Helium will burn into carbon and a few other elements like neon and oxygen. And when that's done, then you'll have a core of carbon. That'll collapse, and then that can ignite and start fusing if there's enough mass to crush it down and get it hot enough. You can keep doing this in stars all the way up to element number 26, iron. Iron works differently. When you try to fuse iron, you could do it, but it doesn't give off energy. It absorbs energy. So all the energy released by this crushing collapse is then absorbed by the iron atoms as they form. In other words, there's nothing left to stop this crushing collapse. So the matter all falls on itself incredibly fast, incredibly fast. Check out the Crash Course Astronomy. I'll let you see the data there, right? So this all happens very quickly. The star slams down on itself and ricochets and explodes outwards. Now this would be a normal star, just a single star all by itself, and it creates a supernova. If we saw a star in the sky, a fairly distant star in our sky that you could see with your naked eye, and it suddenly supernovaed, and it was nighttime and that star was in our sky, it would be potentially almost as bright as day outside. That star would be brilliant for a couple months. So what about the object left behind, though? Well, it exceeded electron degeneracy pressure's ability to hold it. So I want to look at this. If this now, okay, so this was the star, and layer upon layer upon layer upon layer, it was forming iron in the center, collapse, boom, 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 okay, and it explodes. Well, up to a particular mass, what will be left behind? Oh, let's say if that was a white dwarf, no, it's the size of the Earth. This object left behind, can you even see the dot there? The object left behind is the size of a small city, about 7 miles across. Whoa, that's what happens when you exceed electron degeneracy pressure. Now the electrons are shoved into the protons. What do you get when you do that? We form a neutron. Now the star collapses down. And the crazy thing about this, it's a neutron star. Its nuclear density, it's essentially the density of a single giant nucleon. It's the size of like Monticello, a small city. And it has almost all the mass of the star. All the mass that didn't get blown off as this was happening is now there. It's a ferociously massive object. It's as massive as matter can get. A teaspoon of it would weigh like, what do they compare to all the cars in our country, all the cars and trucks in our country? A teaspoon of it would weigh that much, equal to all of the cars and trucks. Okay, a teaspoon of it equaling the mass of a good-sized mountain. Okay, pretty impressive, actually, a very good-sized mountain. It's incredibly dense material. It's unlike anything else we've ever experienced. Furthermore, a star that does that, this is a cute little thing. Every time I tried to discuss this over all these ages, I always dig in my drawer and find an apple that's usually in my drawer. I like apples, so there's usually an apple in my drawer, and I have to ruin it by shoving some pencils through it. Now, why would I do this? It's a kind of bizarre looking thing. Here's the deal. A neutron star, all this matter has collapsed. It has magnetic fields that are beyond our imagination. Absolutely incredible magnetic fields. We know on the Earth that the Earth's magnetic field does not align with its spin axis. It's off to the side, so the magnetic field gets spun around like that. Same thing with a neutron star. So if a neutron star is spinning, its magnetic field is being spun around, not in alignment with the axis. So why does this matter? Well, coming out of that magnetic field is essentially an intense, focused radio beam. If one of these should have its beam point directly to us, then that beam will send a radio pulse at us. Will the radio pulse be continuous? Well, no. The The radio pulse will only happen when that axis aligns with us again. If you imagine an ice skater pulling his arms in as he's spinning, as his arms come in, he spins faster and faster and faster. It's conservation of rotational inertia. Well, that star collapsed from 1,000,000 miles or more in diameter down to 7 miles. If the star used to spin once a month, how fast is it spinning now? It's crazy. It's spinning like once a second. So the way we discovered neutron stars, because nobody was ever going to really say, oh yes, stuff like this is probably in the universe. This is crazy stuff. The way we discovered it is in 1967, Jocelyn Bell, a graduate student working on a radio telescope, this radio telescope received a signal. And the signal went boop, 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 pulsing. We've never seen anything like that from space. What a crazy thing, pulsing. Well, the next day, or shortly thereafter when it was announced to the press, it was called LGMs, stood for Little Green Men, because people were thinking maybe it's like an alien civilization sending a signal to us. But then scientists right away came to the understanding that these signals don't vary in time signature. It's exactly the same time between each one. Well, there's no information in a signal like that. So that would be a really dumb civilization. Nobody we want to talk to. They're just going boop, 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 boop. You can't really do anything with that. They also found another one in the sky. And that one was also going boop, boop, boop. Different time, but also perfect amount of time between each pulse. And they realized this must be a natural object. They dusted off a paper that had been done in the 1930s that suggested such a thing might occur. Nobody ever took it seriously because it's insane. But apparently nature doesn't mind some insanity. And we realized that this object, known as a pulsar, is a neutron star. It's none other than a neutron star. And since then, we found hundreds, thousands of pulsars in the sky, because neutron stars spin. Now, are all neutron stars pulsars? Apparently to somebody, yes. But they're only pulsars to us if they point their magnetic field directly at us somewhere during their rotation. So there's neutron stars all over the place. The ones we can detect easily are those pulsars, the ones whooping us. So that's why I destroy apples in my classroom. So that's a neutron star. The second most bizarre object imaginable. The next object is orders of magnitude more bizarre, because the two ledges that can hold back gravity are electron degeneracy pressure. If you exceed that, you go from a white dwarf down to a neutron star, from something about 8,000 miles across to about 7 miles across. And that's supported by neutron degeneracy pressure. The neutron's doing the same thing. Well, how fast can a neutron go? It's up against the same thing, speed of light. What if there's so much mass, you would require those neutrons to go faster than the speed of light? In that case, we'll make this now, we'll make this the neutron star. If that happens, I need some black chalk. If that happens, this will, if it exceeds the neutron degeneracy pressure, this will start collapsing again. But you've blown past the last ledge. So what's going to stop it collapsing now? Nothing. Nothing. It will collapse forever. Well, wait a second. How small can it get? Apparently, there's not really a limit. However small it currently is, it could get smaller. And however small it'll be tomorrow, it could get smaller and smaller. And all the mass of the whole star, or much of the mass of the whole star, all collapsed into an area infinitely tiny? Okay, that's crazy. That's crazy. But we can never see that object, that super tiny object. You can't see it. Why? Because the gravity of it is so incredible that somewhere right around here, it forms a black hole. Please understand, the black hole is not the thing. The black hole is the effect of the thing on the universe. The black hole is the region of space where the gravity is so intense it exceeds the speed of light. So no light can escape it. The actual object that's causing that, how big is that? You can't give a size, because whatever size you would give, however small you would say, tomorrow it's going to be smaller. It will keep shrinking. Why? It's blown past the second ledge. There is no third. There is no other pressure that matter can exert upon itself, and it gets infinitely tiny. If this seems insane, you are in good company thinking it's insane. Albert Einstein, when presented with his own mathematics that showed that such a thing might be possible, said, the math is correct, but I can't believe that nature would ever allow such an insane object. He said that. Later on, we discovered such an insane object, and we've since discovered them all over the place. There are two kinds of black holes that stars turn into, and black holes you get apparently by colliding millions of stars together, and they're in the center of apparently, quite possibly, every galaxy has a supermassive black hole on the order of millions of solar masses, upwards of billions of solar masses. These things also don't really have a size limit. They could keep eating more matter, consuming other black holes, if you can imagine such a thing. But they can do it, and they get bigger and bigger over time. Now, again, the thing inside is infinitely tiny, but the region of space where you've exceeded the escape velocity of light, so it's the black hole effect itself, gets larger and larger till these in the center of galaxies truly become huge. So what are the three objects? White dwarf. It's relatively similar to normal matter, but incredibly compressed. Teaspoon there weighs as much as, I think, like 13 bull elephants. Pretty impressive. There's a surface there, right? It's about the size of Earth, spinning very fast, mind-boggling object. That's held up by electron degeneracy pressure. If you exceed that, it collapses down to an even more mind-boggling object, the neutron star, held up by neutron degeneracy pressure, about 7 miles across. They say 7 to 10 miles across. The more massive it is, the more gravity has pulled it smaller. So the more massive neutron stars are actually smaller. Okay. If you exceed the neutron degeneracy pressure, you go down to a black hole. Now, the scientists who talk about this will say at least a neutron star, as bizarre as it is, has a surface. Now, if you stood on the surface, you'd disappear immediately. Check out what Phil Plait suggests. But a black hole doesn't even have a surface. There's nothing to stand on. Our brains don't work with this stuff. And yet, fortunately, our mathematics and our science does. So those are the three potential objects. Listen carefully to what Crash Course has to say about them. The two ledges, electron degeneracy pressure, neutron degeneracy pressure. That's it. You blow past neutron degeneracy pressure, you collapse forever. Hey, thanks for listening. Bye-bye.